Hey everyone, thanks for tuning into the demo today. We will talk about vision transformers. Transformers are an architecture which is normally used for sequence to, or is used for sequence to sequence tasks. They were discovered or proposed in 2017, and historically they've been used for natural language processing tasks, such as translation or next word prediction. However, because encoding text requires a lot of overhead, we'll be working with transformers on images today. But I promise we will use a different data set than FastMNest or MNest. We're going to be using a more general image data set called Caltech 101 with more classes and more objects. So at the core of a transformer architecture, really the thing that makes it special is an operation called self-attention. Self-attention is a mathematical operation that we've covered in the lecture before, but I'm going to go over it one more time here. The idea is that the input will be a sequence of different things that I'll call tokens. Each one of these tokens is represented as a vector. So we have the vectors x1 through xn. So there are n things in the sequence, and also the dimension of each one of these vectors is m. So this is our input, x1 through xn, and we're going to create some output, which is y1 through yn. Notice that the length of these sequences is the same. So I have the same number of tokens in my input as I do in my output. In this case, I'm saying that the dimension of each one of these vectors is the same as the dimension of each one of the vectors in the output, but this doesn't have to be true in general, as we'll see shortly. The self-attention operation builds the output sequences or the output tokens y1 through yn by combining the input token. We'll consider a basic level of this operation just now to get a feeling for it. And mathematically, we write yi, so each one of the output vectors, as a sum over each one of the input vectors, where we're weighting the xj component by a measure of how similar xi and xj are to each other. So this is the xi transpose xj is the inner product between vectors xi and xj, which generally, up to scaling, denotes the similarity between two different vectors. So in this way, yi will have larger components of input tokens that it's similar to. So if xi and xj are close, there will be a larger weight on xj. If xi and xj are far away from each other and their inner product is small, then there'll be a smaller component of xj in the output here. Okay. This intuitively gives the idea that I'm building the output as some combination of the input. And a very nice way to think about this is in translation from one language in one sentence to, a sentence in one language to a sentence in another language, where each one of the words in the other language is some combination of the words in the starting language. If you'll look closely, you'll notice that the input token appears 3 different times in the definition of the outputs. So one time here, it acts as a query, querying how similar xi is to xj. Here, it appears xj as a key for similarity. I'm asking the question, how similar xi is to xj, the key, and also as a value, where I'm building the output as some linear combination of the input vectors. We, in general, can think of each one of these different ways that xi and xj appear as performing a different task. We have a query task, a key task, and a value task. When we run self-attention, we can generalize this by passing each appearance of the input through its own fully connected layer to make it special. So instead of just having xi appear in 3 different places, we'll rewrite this function in terms of qi, kj, and vj, where we're defining each one of these based on the input sequence, and we're just passing it through, in this case, a fully connected linear layer, which may or may not have an activation on top of it. Okay, so this is the general form of self-attention, where I'm looking up based on this query, which is based on xi itself, how similar it is to this, the jth part of the input, which is I'm looking up based on the key value. And then based on the similarity here, I'm adding up the vj vector, which is a function of the starting vector xi. Notice that this operation is exactly the same operation we have up here when the W matrices here, which are learnable parameters, when each one of these is the identity, it recovers the same thing we have here. So intuitively, I'm building the output as linear combination of the input. It's just now I can modify each one of the places that the input appears by passing it through its own special neural network. Now, it often makes sense to think of this process in the context of natural language processing, in particular translation, as we mentioned before. But today, we'll be talking about this in the context of images. So transformers were introduced in the popular paper Attention Is All You Need. And for the first 3 years, they were primarily used for natural language processing tasks. There are really 2 reasons for this. One of them is that it wasn't clear to how to encode images into sequences or use a sequence output for a task such as classification. The second reason is that vision transformers seem to need more compute and data than convolutional networks. So it just wasn't feasible to run lots of experiments of transformer architectures on images. But 3 years after they were first proposed, transformers were used for a vision task in a very cleverly titled paper called An Image is Worth 16 by 16 Words. Like the title suggests, the paper turns an image into a sequence by partitioning it into equally sized parts. So this is a starting image. We will turn this into a sequence by considering each one of these different partitions of it, disjoint pieces. I'll call these patches. And then the sequence consists of these different patches that were initially in this image. So that was the way that they solved of turning the image into a sequence. Once they had the sequence, they passed this through a linear layer, and they got these different patches, which they can then pass through a standard transformer architecture. The standard transformer architecture consists of everything we're familiar with, so batch normalization layers and multi-layer perceptrons. They're just fully connected layers, and skipped connections to make it a residual network. But the new operation they have is this multi-head attention, which is exactly the self-attention operation that we just described. Okay, so we can run a transformer on an image by converting the image into these different patches and treating the sequence or the tokens in the sequence as each one of these patches. We can then pass this through a transformer encoder architecture, but then the natural question is, how do I interpret an output classification as from a sequence of things? The way they solved that problem in this paper is that they gave it one more input token into the input sequence, which consists of an extra learnable class embedding here. And then you run this operation where basically self-attention and the different layers are telling you how similar, you're allowing it to extract information by saying how similar is this part of the image to the other parts of the image. And then I build the output by a weighted combination of everything in the input based on how similar they are to each other. So for example, here, this part of the image looks similar in some sense to the clouds and definitely similar to the architecture going on here, and maybe less similar to the sidewalk and the shrubs here. So when I pass this through an attention layer, I'm getting the similarity of that particular patch of image to everything else, and that allows me to build an output. And then also one of the things I'm applying this to is this class token. And this class token will look at the similarity between this class and everything else in the image. So in some sense, the class token will select out the object which is inside the image, and based on that selection of that object, we can then classify what's in the image. You can kind of think of this as related to a standard convolutional neural network, where I'm extracting information from a network by comparing each one of the pixels to everything around it. But the difference here is that instead of being limited to everything that's directly surrounding me, I can compare this particular patch to everything else in the image. It's just by using positional embedding, which we won't talk about here, I am closer to everything that is closer to me. So this part of the patch will be closest to these 3 things that initially surround. Okay, great. So this is how we apply attention and transformers to a vision task such as classification, and that's what we'll be doing today. Unfortunately, so it is possible to train a simple vision transformer from scratch. That's not what we'll be doing today. We'll be using a pre-trained version of this. If you're interested in training it from scratch, there is an old demo which is linked to right here that you can check out. Today, we'll be using a pre-trained transformer architecture, which is quite large. It has 11 different layers of this thing. And we won't be doing any training on it because it is very substantial, but instead we'll just be doing inference. We'll be taking an image from a different data set, passing it through and seeing what classification output it gives us. And then we'll also poke into the architecture a little bit and maybe get a sense for these similarity weights between the different patches, so the xi and xj. And that'll be nice because it'll give us some insight into the classification process. So let's jump in. I'm not sure if we've talked about this in the demo before, but hopefully you've seen it so far. Basically, the idea is that there are two different architectures we can use to evaluate and train our neural network. One is our standard CPU, and another is a GPU, which is called a CUDA in PyTorch. This operation just checks which one of these is available, and it calls that the device. Then when we are evaluating a model, we'll put our data and the model onto the device, which is the GPU if we have it. And then if we have access to a GPU, everything will run faster. Okay. The transformer we'll talk about today was trained on the ImageNet dataset, but the ImageNet dataset is quite large, and I wasn't able to download it easily for the demo today. So instead, we're going to be using a similar but different dataset called Caltech 101. There are lots of datasets which PyTorch makes easy to load using functions like this, and you can check out the list of them over here. It's very nice. There are lots of them. So you can see there's like fashion MNIST, and there's like one with aircraft and a bunch of other images, or a bunch of other vision data sets that we have here. Okay, so I chose to use Caltech 101, applying a standard transform to it. I download it and I make a data loader from it. Let's take a look at it. I will get the images and the labels from one of the batches of the data loader, and then I define this function, which will just plot things for me. So in this case, we're just plotting each one of the images that we have, along with the label which is in this data set for it. So it looks like 5 corresponds to maybe airplanes, and 2 corresponds to a lion or a cat or leopard or something like that. There are lots of different things in this data set. And the catch, though, is that we won't be able to evaluate the accuracy of our model directly because the Caltech dataset has 101 labels, and the model that we're using was trained on ImageNet, which has 1,000 labels, and these labels do not necessarily overlap with each other. So 12 in the Caltech 101 dataset does not overlap with 12 in the ImageNet dataset. We'll load a text description of the 1,000 images from here. This just says that like the 20th thing in the ImageNet dataset corresponds to a water ouzel, a dipper, etc., and it has all 1,000 one of these. It looks like 999 is toilet tissue. Okay, so I'm just loading that and I put it in this dictionary here. Now that we have some way of interpreting the output of our model that we're not training, we're only using it for evaluation, then we'll load it with the default pre-trained weights here. Once we've loaded it, let's poke around and take a look at what's going inside. The first step here is that we are applying a 2D convolutional layer to our starting image. Each one of the kernel size is 16 by 16. So this is the way that we're converting an image into different size patches, and then we're going to pass those patches through our transformer architecture. The transformer architecture consists of an encoder, which has tons of different layers in it. Each one of these encoder layers has a batch normalization and self-attention. This is the special operation which makes transformers different from other architectures. We apply layer normalization, and then we apply a standard block where we have a few linear layers and some dropout and a GELU, which is Gaussian error linear unit. Okay, which is just a different kind of activation that we can apply on top of it. Okay, there are lots of layers here. In fact, there are, I believe, 11 different layers. Once we finally pass it to the end of these layers, we now have a sequence representing this image. We will take just the first thing in the sequence, which represents the dummy class input token. and then we'll apply a linear layer to that. So we'll go from 768 dimensions of these features to the output features, which is 1,000. Again, it's 1,000 for each one of the different classes. That's our model. Let's count the number of parameters. There are 86 million different parameters in this model, which is quite a bit, which is the reason that it's not realistic for us to train it in a short period of time. One thing we could have done is just replace this linear head with another linear head, which goes from 768 to the number of output, or the number of features, or the number of classes that we have, which is 101 instead of 1,000. But this would have required a lot of training because we have lots of classes there, and I don't think it's worth spending the time on that. Okay, when we actually want to do inference on this, it's very quick, or comparatively quick compared to the training process, but still much longer than other models that we've seen. We'll put our model and our images onto the device. If we print out the device here, I think we're working with a CUDA. Yep. We connected to one of the runtimes that has a CUDA, and still it takes a while. So that tells you like how big this model is. We get an output. If we look at first, maybe let's look at the image's input shape. So this, it looks like the batch size is 16. These are colored images, and each one of them is 224 by 224. We go from this input to this output, which is same batch size. That's great. And now we have a 1,000-dimensional vector for each one of these representing the different classes. We'll convert these classes, we'll convert this vector into classes by picking the maximum one of these. So if we look at output 0, so this corresponds to the 0th image. Each one of these is a different value. We'll take the largest one of these values and we'll say that's the class that the model is predicting for that particular image. Once we do that, we will convert that class into a text string which describes it using this dictionary that we loaded from that handy file that someone put on the internet. Now we can use this function to plot what we have here. Notice that we're using a different the set of class labels that we have that our model outputs is different from the set of class labels that are inherent in the images that we passed in here. But it looks like it does pretty well. So it says this is a tiger, it knows that these are leopards, it calls this an airliner and this a warplane. Maybe that's a misclassification, or maybe it knows like a different type of warplane here. Interestingly, it looks like the ImageNet dataset doesn't have any people in it. So we have a picture of a person here, and instead of outputting person, it outputs bookshop, which is actually correct, or very reasonable, because if you look in the back here, there are a lot of books. So the model doesn't know what a person is, so it doesn't output that class, but it does know that there are books here, and it outputs bookshop as the class that it's predicting here. Here it also says cassette player when this is a camera, but maybe that's like a different interpretation. It says notebook here, but if we look at what notebook corresponds to, another description of it is notebook computer, which is maybe arguably correct for this one. Okay. So let's just say there are some errors, but a lot of that is because the ImageNet labels are not a superset of the Caltech 101 label. So it just doesn't know what some of these things are in the input description. Nonetheless, things like this are very impressive. It doesn't know what a person is, but it can look in the background and figure out that there are books there. Yeah, bookstore, bookstall, cool. Okay, so this model clearly works very well. Instead of just looking at the output, let's try to take a look at one of the self-attention layer heads. And in particular, we want to look at the weight matrix, which is the similarity between each one of the input tokens. This code right here is the code which is equivalent to running the, which happens in the forward pass of this model. I found this by poking around in the model that we inherited from. In particular, I think that Vision Transformer, yep. So this is like the class that we're using. And if we look at the forward pass, this is what's going on. So that's the same code that we have over here. We are interested in processing the input the same way it's processed in the in the standard model, except instead of just applying all of the encoder layers to this variable x at this point, we want to take x and pass it through just one of them. So if we, let's first look at the shape of x. X is batch size by 197 by 768. The reason it's 197 is because we've added one class dummy variable to the input sequence. And before that, we had 196 different classes, which is the square root of that is 14. So it looks like our model has turned each one of these images into 14 patches where there are 14 rows and 14 columns in it. We'll visualize this shortly. So there are 196 patches representing our image, plus one more in this input sequence for the dummy classification token. Each one of these is represented in 768 dimensions. So n in our case is 197. That's the number of things in the sequence, and 768 is the dimension of our the dimension of each one of these tokens. So if we look at our model again, and we look at the encoder layer, the way we define this encoder layer is we apply some normalization to it, and then we pass it through a multi-head attention. By poking around again in this source file that defines this model. So I think class encoder block, yeah. When we do the encoder, the forward operation consists of applying this normalization and then this attention layer to it. In our case, when we apply this attention layer, we're applying it 3 times to the same input sequence. That's what makes it called self-attention. If we were passing in different sequences, so different things for the keys, queries, and the values, then it would be a different set of, it would be a different self-attention operation. Or it would be a different attention operation, which is no longer self-attention. Here, I'm asking for the weights back. The weights are the similarities between each one of the things in the input. So if we look at the shape of the weights, it's still the batch size. It's now 197 by 197. So each one of the things in this matrix is the similarity between the ith thing in the input and the jth thing in the input, or these are our queries, our keys and queries in the self-attention operation. So this in itself is not particularly interpretable. I could try to plot one of these. So I can do that right now. Actually, plot imshow. Let's look at the first one of these, and then I'm just going to permute it so that we can plot it. And I think I need to put it on the CPU, and probably don't need to detach the gradient. Oh, that's not going to work. I get an error here. Number of dimensions, it does not match the length desired. Oh, right, that's silly. I don't need to permute it because it's just 197 by 197. Okay, so I need to do detach and then apply. Okay, when I run this, I get something which is not that interpretable. It's just the similarities between different things in this input. But really, one thing that I could care about is a similarity between the classification token, which is the first one of these, and everything else. So I'll extract that from this matrix by looking at just the first row here and looking at the similarity between that very first input vector, which corresponds to the dummy classification token, and the rest of the things in that column. This, if I just do this operation, this will not be the right shape. This will be 16 by 196, which is not something I can visualize. So I'll reshape this, which will just change the dimension of this so that it's 14 by 14, and I can plot it as an image. Once I do these classification weights, I'm going to plot them next to the original starting images that we had, and I'll also look at the predicted labels that we have here. So, for example, this is our airliner image, and this is the similarity between our classification token and each one of the different patches in our image. By looking at this, you can kind of see that, for example, someone pointed this out in the in-person demo, the engine here looks like it's showing up as something which has a high value or a high relationship with the classification token, which is saying that the classification that we're making, an airliner, has a high relationship with the fact that this thing has an engine right there, which makes sense. So in some sense, it's very interpretable. I'm looking at different patches in this image, and I'm saying how similar are those patches to the classification I'm making. On images where there's really only one object on it, this is very clear. There's a high overlap between the actual leopard in this image and the classification token. You can kind of see that for the different things that we also have here. Like here, it's lighting up maybe on the tail light of this car, and maybe by like the hood of this car, which is telling it that this is a minivan. It thinks maybe it doesn't have a classification label for a car. Remember though that this is just at the first layer of this encoder architecture. We could also do this after applying it through all like the first 10 layers and then looking at the last self-attention layer. If we do that here and we get the output weights and we define the classification weights in the same way, and then we can plot these and maybe it looks slightly more defined here. So for example, this leopard is like highlighting on maybe the leopard's head there. Here it looks like it's highlighting on like different parts of its back, maybe because there are like spots there. The revolver, as before, there's only one thing going on in this image, so it's easy to detect it. And then the minivan, it looks like it's more highlights on the front of the car and on the back of it. And maybe the crawfish looks a little bit more defined. So the cool thing that I want to stress here is that this is an emergent property of this model. Nothing that we've done has trained it for this behavior. It's just that if we look at the classification token and we compare it to the different patches of the image, it highlights over the different parts of the image which correspond to the output that we're giving it, which is a very nice feature of this. And I hope this has been helpful and interesting for you as a way of understanding transformers, particularly in the context of visual image classification tasks. I look forward to having you tune in next week. I believe, let me check right now, we will be talking about Word2Vec, which is a way of encoding words into a vector representation so that we can apply machine learning models and tools to them. Thank you very much.